Hi, my name is Tom Brown. I'm the director of Borderland Sciences Research Foundation in California. And today we're in our top secret laboratory hidden in the vast suburban wastelands of Southern California. And we're taking a look at Tesla's longitudinal electricity. The electricity in general use today is transverse electromagnetism. And what Tesla was experimenting with in his types of experiments was called longitudinal dielectricity, a polar opposite to that. And we're doing advanced research into that type of electricity. Now we'll take a quote here from the book Experiments with Alternate Currents of High Potential and High Frequency, which has an appendix called The Transmission of Electric Energy Without Wires. And to quote Nikola Tesla, toward the close of 1898, a systematic research carried on for a number of years with the object of perfecting a method of transmission of electrical energy through the natural medium led me to recognize three important necessities. First, to develop a transmitter of great power. Second, to perfect means for individualizing and isolating the energy transmitted. And third, to ascertain the laws of propagation of currents through the earth and atmosphere. Now, the transmission of great power was, of course, carried on by Nikola Tesla in his Colorado Springs experiments, which led to the building of the Wardenclyffe Tower, which was to transmit electrical energy around the Earth. And the second point, the means of individualizing the currents, was in his experiments with harmonic resonance circuits, such as you're going to see today in this video. And third, the laws of propagation are his one-wire and wireless power transmission, where he demonstrated longitudinal currents rather than the transverse currents, which he did not feel were all that swell for propagation of electricity. So here today we're going to see some experiments in this, and now to give you an introduction to the experiments by showing Tesla's patent and the schematic that we're using is Peter Lindemann, Director of Borderland Sciences.
Hi, I'm Peter Lindemann, Vice President of the Borderland Sciences Research Foundation. Today I'm going to explain to you the basic experimental setup, which we're going to demonstrate in a little minute. Over here we have a schematic drawing of our experimental setup. And down here, I'd like to first bring your attention to Nikola Tesla's patent number 649621, which was granted on May 15th, 1900. Basically, this describes the experimental setup which we will attempt to show you today. And I'd like to describe it for you right now. This is a transmission and receiving system for what he called his wireless power transmission. The exact name of the patent is Apparatus for Transmission of Electrical Energy. And it consists of a generator system which produces the appropriate types of currents, which goes through a two-loop primary on this device here. This is the thick, darker line around, which you can see on your television screen. Inside here is a flat spiral coil, which is connected to ground at the outside of the spiral, and on the inside of the spiral is attached to what he calls the termination, which in the case of the Colorado Springs experiment was a ball, a sphere that was high up in the air. The receiving apparatus is identical in nature, consisting of a termination, a flat spiral coil, and a connection to the ground. And the outside primary or secondary of this system is attached to the loads. So that describes the patents, the patent that Tesla was granted in 1900. Now what I'd like to do is describe for you the exact apparatus which we will be testing for you today. Our generator system consists of this much of our diagram here, which includes a medical Tesla coil circa 1920, which produces our supply of electrical induction. We also have a capacitor to create circulating currents in this, which is a 0.001 microfarad, 15,000 volt capacitor built by the Faraday Corporation. And we have two hydrogen spark gap tubes, 1B22 here. And this creates a negative resistance which helps to accelerate the wave. So this is what we're using to supply the appropriate currents to our primary of our coil here, which is a two-turn flat coil made out of sheet copper. This showing the two turns, just like the two turns shown in the diagram here. Our secondary is made up of, our termination in this case is a neon bulb, which acts as a plasma, which in these low power systems works better than a large sphere. That's connected to our flat spiral. In this case, our flat spiral is made out of Teflon-coated silvered coaxial cable, of which we're just using the outside shielding, the silvered shielding, and not the inner wire, because these currents operate primarily using what's called the skin effect. And then our output, which is at the outside of the flat spiral, our output here. And now we will run a number of experiments attaching various things to our output here, showing various behaviors. Our second apparatus is identical. It has an input at the outside of the flat spiral made out of silvered coaxial with Teflon coating on it, and going up to a second termination, and a second series resonant harmonic resonance circuit, which is tuned exactly the way our transmitter is, with two turns of flat copper sheet and connected to a second 0.001 microfarad capacitor identical to this one. And so these two primary circuits, one of which is energized, the other of which operates in harmonic resonance, makes up our circuit. We will attach loads to this output, as well as putting various devices in here for the transmission of our electric currents. So this is our test setup. And now I'd like to introduce Eric Dollard, who will first show us the actual physical setup of our test apparatus today, and then we will run the experiments. Eric?
Hi, my name's Eric Dollard, and I'll be running the experimental setup for the Tesla wireless transmission system. We'll go through our diagram here on the board, which Peter showed a little earlier, but now we'll show you the actual devices. For a supply of electrical induction, we have an old Fisher Medical Tesla coil from roughly around 1920 to 1930, which in itself is a complete little wireless transmitter, but we're just going to use it to charge up our high voltage capacitor shown here on the diagram, which is an old mica capacitor from shortwave radio transmitters used also around the 20s. We use these kind of capacitors because they have a very low inductance and very low hysteresis losses, and can deliver really strong high power impulses. And here's our 1B22 hydrogen fibertron tubes that we're using as spark gaps. You can use a number of other things for spark gaps, such as quenched gaps or rotating commutators with these tubes. Work pretty good for this, and they don't put out a lot of light or noise, and the negative resistance of the hydrogen plasma increases the rate at which the discharge occurs and produces stronger transients. Our primary coil is two turns of copper right here on the large transmitter unit. Let's hold this up a little bit. You might be able to see actual strips of copper on the primary, and then our secondary resonant coil. And of course our coil is shown here on the diagram. I might want to point out that this coil is not just a simple inductance coil, nor is this thing just a simple transformer. The inner turning capacitance plays a very important part in this coil to give it a very strong resonant frequency. And the resonant frequency of our primary oscillating circuit here is chosen to fall on one of the fundamental harmonics of resonance of this complex network of mutual inductions and capacities which the spiral makes up. And we'll go through a frequency sweep and what have you later to determine exactly what these are. Our termination is an argon bulb here at the top. And our output terminal on the outside of the spiral comes down here to a little banana plug which we can plug various things into. This coil here serves as a loading coil to help couple the energy out into the rest of the system, increase the efficiency. So this basically would simulate maybe the impedance of the earth or the transmission medium in general to give the coil something to work into. Okay, to start off with, our transmission path is a simple plasma column, and then we have our conjugate receiving coil, which has exactly all the same characteristics except it's wound in the opposite direction. And it finally ends up with its final tuning capacitor, the same tuning circuit as the primary, so naturally we're going to get flow between the two because of their resonance, and then we have the end result, which is a 15-watt light bulb, which will be our resistance load. We'll connect across the output here. And we'll have Tom turn the switch on and we'll see it go. So of course the load is lit, and we have a single wire path going from the receiving transformer through the plasma column, through the loading coil, and off to the transmitter coil. Hence the single wire method of electrical transmission. Okay, we'll take a brief pause here and we'll get into our experimental setups. Okay, our first experiment is we'll run the light bulb conventionally in the electromagnetic fashion where the circuit is a closed loop or a true circuit. And then what we're going to do is we're going to pull the plug and see if the light bulb still lights up. And we'll start off with the conventional circuit method, energize it, and of course the bulb lights up. Now what we're going to do is we're going to pull the plug on the bulb. We find the light bulb still lights up, so we're starting to get a rather novel thing going on here. You can see the wires become quite energized. High voltage is on it. The neon bulb readily indicates there's quite a bit of charge. Okay, turn off the power. Now what we're going to do, let's go back to our diagram here. What we did in disconnecting the plug is we switched to this configuration here where there's no connection on the other end of the light bulb. Okay, now what we're going to do is hook an amp meter up to ground. We have a Weston, or Simpson in this case, thermo amp meter, which is not very susceptible to spurious readings because it takes actual heating to produce a result. And we're going to plug this into the output end of the coil and see how much current this system delivers to the ground. Reference to our drawings over here, this is now our setup. And if we energize the system, find that we have roughly 0.68 amperes of current flowing out of one terminal in the ground. Hence the Tesla wireless transmitter. Turn off the power. Okay, and after a brief pause, we're going to go through our experiments where we hook various devices in between the two coils and see how they propagate these currents. Okay, now we have our two coils set up with our series path, our terminals. In this case, our terminals will be here on the workbench. terminal from the transmitting end through the loading coil, and the terminal to the receiving end, and of course we can connect various items in between. And at the receiving end we have a pickup thermomilliamp meter to measure the amount of induction the device is receiving, and that'll be our determination of how effective each of our three items are here for the transmission of currents from the transmitter to the receiver.
So can you just describe this situation here? What do you got? You've got two turns of
14 gauge wire and a little magnetic pickup coil that determine how strong the field is around the coil. And of course that gives us an indication of how effective each of the items is in conveying the current from the transmitter to the receiver.
All right, great.
Okay, we'll start off with just a regular wire connection and go on the power supply, and that will give us the reading on the milliamp meter, which is, can you read it, Peter?
About half scale. Looks like 72 milliamps.
72 radio frequency milliamps. Okay, we'll turn the power off. The next thing we'll put in is a plasma column. And we'll energize the power. And the meter will read again.
Slightly less, about 65, 66.
Okay. The next thing we'll insert in is a series parallel bank of incandescent bulbs.
Now it's a lot lower, about 50 milliamperes.
Okay, so we can see now we have a definite difference between transmission through a plasma column and transmission through what would represent an effective length of conventional transmission line, in other words, wire with resistance. Plasma column tends not to have any resistance, where the conventional transmission medium tends to exhibit resistance. And of course, in direct connection, all these factors are so small that they don't really appear. Now, what we're going to do is we're going to get into some of the effects of the illumination that comes off of these incandescent bulbs, which contain vacuum, when run off of these currents. And we're going to do a comparison between a bulb running off of 60 cycles and a bulb running off of high frequency right next to each other. And this will lead us into our second Tesla patent, which is the transmission of electricity by radiant means. And we're going to show how DC can flow through space with only one wire. So we'll take a brief break here and set up our new experimental apparatus. Okay, here we have two conventional light bulbs, and they're 15 watt, 120 volt. We'll bring one up close to the camera here so the construction of the bulb can be seen.
It's too close. Yeah, just back there is fine. And I'm going to get a sharp focus on this. You have to go farther away even. They're about there. That's fine. Yeah, so you can see the filament. It's a little ring filament. That's great.
Right, and one interesting feature of these bulbs is they have a very big vacuum space, which is not usually found in most light bulbs, and they're not filled with gas like most light bulbs are. These are vacuum light bulbs. So we'll have two of them here. This one and this one. One will run off of conventional 60 cycle alternating current, and the other one will run off of the longitudinal current. And we can see the brightness is pretty close to the same. Now let Tom come over and see if he experiences any difference between the light of the two bulbs.
Okay, well, one thing I do notice just visually, and we really can't record this because we don't have the proper detectors, but just the character of the light. This the electromagnetic light, transverse, looks somewhat reddish to my eye, and this looks somewhat bluish. And it just feels kind of hot, like a regular bulb. But around this one here, I feel a pressure coming off, a charge and a pressure, which I felt a little shock there also. And but the character of the light is definitely different. There is a distinct pressure, and the higher up we turn the power going in, the stronger the pressure is. And now we'll give another demonstration which shows another characteristic of this opposite to the pressure.
Okay, one other thing I'd like to point out is the fact that this situation over here is very stable and quiet. We have, according to the Variac, 115 volts across the bulb. This light bulb here, the socket, is arcing over inside. indicating there's several thousand volts across the bulb. So we can start to see some difference happening here. Now what happens is when you have gas in the bulb, as well as the filament, this very high voltage that appears across the bulb energizes the gas, and you end up with what would be a full spectrum light bulb, which still retains its incandescent characteristics. But these bulbs being vacuum, we can't really fully demonstrate this. Now what we're going to do next is we have a force coming off the bulb, then we can study this force. And what we'll do is turn the power off for a second here, and we have a little piece of copper strip dangling from insulated tape. Let me just center this up here a little bit. I can help.
No, it's got to be lower.
Why not?
How did it get over
Okay, first we'll bring the strip near the Tesla current bulb. Turn it on. See the traction.
Let me turn it off on a couple times. Yeah.
Move it slightly farther away, and let me get a real tight focus on
Turn the
this.
power on. I'll bring it near it. We'll see where it folds in. You see once you hang it on there. Okay, now what we'll do next. Stuff.
So that's just a piece. That's a piece of copper foil,
Copper foil, copper tape,
hanging on a piece of
masking tape.
masking tape.
Turn on the conventional, and of course we see we get no effect.
Even closer, right?
Right up to it, and as can be expected, there's really not much of anything happening there.
Right. Okay.
Just a little bit of residual charge that was left on the metal. We'll go back to this one, and we can see traction. Okay, we'll turn the power off. Now we can say, well, it's just high voltage. But what we'll do, we'll put this point here.
So now once you're bypassing the light bulb,
Bypassing the light bulb.
so we're just running the current past
just
the
going to
strip.
have the high voltage itself next to the thing.
Okay.
Turn it on. No traction. So as we can see, it's definitely charged there. Bring the point right up to it. No desire at all to be attracted to it.
So what you're saying is that the attraction is related to the action that's happening in the bulb.
Right. The bulb is producing rays. As well as light rays, it's producing another form of ray which exhibits mechanical action at a distance. The human body experiences it as pushing out, but material objects experience it as pushing in.
Okay. Can we see that effect one more time? Let me start with it just a little bit farther away. We can turn this just so we can have an idea. And let me just focus right tight in there. Okay.
Ready?
Pulls it right in.
Here it goes.
Okay, now what this does is bring us to a whole new area of Tesla's wireless power transmission, which we'll get into part 2. And we'll go back to the original patent and start out from there. So we'll take a brief break here.
Okay, here we're looking at Nikola Tesla's patent number 685957, apparatus for the utilization of radiant energy. Now, what Tesla was very interested in was the propagation of light and currents, beams of light and current through space, and also on how to receive these, both send and receive. And here we see the apparatus for receiving, which is basically a small condenser, one end to ground, the other end up into space. And you could pick up various cosmic radiation, such as solar. And Tesla also claimed that some of these radiations from outer space moved at 50 times the velocity of light, although there's no exact verification of that. And here we see an apparatus, a carbon arc, charging this. And down at the bottom here we see a light bulb, single wire bulb, energizing the apparatus. And what we're going to do now is show you this experiment, charge a capacitor from a bulb, and show you the discharge from it.
Okay, what we have here is a capacitor, television doorknob capacitor, 500 microfarads at 20,000 volts, and it's connected to ground, sink. In the other terminal of this capacitor, we're going to bring near this light bulb and see if we can charge the capacitor up like Tesla did with the radiations or forces emanating from the light bulb. So we'll energize the circuit, and we'll hold the other pole of the capacitor some distance away from the bulb. Okay, let's see if we get a charge on it. We have a small neon bulb here. Capacitor seems to want to go away. I don't know if you caught it.
Small
Yeah,
flash.
just a small flash on the neon bulb.
Let's do it once more.
So let's start by shorting the capacitor completely to handle the doubters that we don't start with a charged capacitor. Okay, so that's completely shorted to ground, both ends, so that you can believe that this is an absolutely dead short. It's an uncharged capacitor.
Prevent it from rolling away. Okay, let's try it again.
This time let's leave it near there to try and build up a bigger charge.
Yeah, I haven't determined exactly what part of the bulb is out the best charge yet.
And bring it down by the side so it's closer to the cylinder.
The sides is where I feel the greatest pressure.
Yeah.
Okay, I think that'll do it.
Okay, and we'll try and keep the neon bulb in our view here, so if it flashes at all.
Little
Very
tiny
small
flash.
flash that time. Let's try it one more time. Okay, let's try it again. One time I got a very large snap out of it. Yeah,
There we go.
pop.
Okay.
Okay, so what it wants is to be held one more spot, or one particular spot, not moved around. So it indicates the charge is different in different directions. Okay. Now, what we should do is bring it near the wire, or one of the hot points around here, and make sure it's not just the electricity itself that's charging it up. Corona there, indicating the currents are flowing to the capacitor. Very small flash. Let's try it one more time. Corona is going to cause a certain amount of rectification because it's an electrical conductor, so we will expect a small charge to exist on the capacitor. Now we'll go back to the light bulb. Okay. Snap. Definite difference. Okay, one other experiment we'll do is we'll bring it near the very high voltage of the neon or argon lamp. And there'll be some residual charge, I'm sure, but no snap. And we'll go back one more time. The light bulb. Pop. Okay, now what we're going to do next, our next test setup, is we're going to attempt to demonstrate the actual transmission of DC through free space.
So basically what we've just seen here is that fairly conventional light bulbs produce radiations which are not seen when the same devices are run on ordinary 60-cycle AC
That's
electromagnetism.
correct. Right.